Welcome to our lecture on energy transition. Today we'll talk about wind power or wind energy. The use of wind energy is rather old. Since thousands of years, wind energy has been used for grinding corn and for lifting water. Here you see a wind power pumping system in China. Here you see a horizontal axis a windmill from Spain, typical Don Quixote windmill, 1400 Anno Domini. You'll find here the development of technology of wind power. So the first wind turbines in 1980 got a typical power of about 30 kilowatts, a rotor diameter of 15 meters and a height of 30 meters. Then they steadily increased. So did also the annual energy yield, because if you get to a higher value, there is even more wind, but also more constant wind. This is an additional advantage. And so the annual yield is disproportionately increasing with the height and the area, as you see here. And the actual development is that you have for offshore even wind power plants with a power of 12 megawatts. They are too expensive for onshore use, but due to the high maintenance costs offshore, they make sense as an offshore wind turbine. Usually you have onshore the limitation between 6 and 8 megawatt. Here you see the components of a wind power converter with a gear. More modern one, which we see later, can work without a gear. The wind is captured by the blades. Then the blade has an aerodynamic form which creates a lift and is creating a moment to turn the turbine around the axis. You can adjust it at all modern windmills by the pitch. Then you have the low speed shaft, while normal generators with pole pairs of 1 or 2 need either 1500 or 3000 rounds per minute. You have to have a gear to do that, or you have a special generator with a lot of poles, so you can work with a low speed shaft. The turbine has to be directed actively into the direction of the wind. So you have a wind vane which measures the direction of the wind, and then you have a yaw motor or Azimuthal drive which directs the hub into the direction of the wind. This is now a wind turbine with a generator with a high number of poles, so you don't need any gear anymore, so you have less problems with the gear, less maintenance, and also a higher efficiency. The problem is more heavy and more costly. Where is the wind coming from? Actually, it's solar energy. Around the equator we have more solar irradiance, so we have a higher heating there, and this leads to a buoyancy of the air there and is lifted up, and there is cold air flowing from the north and from the south again there, and these movements are called winds. So accordingly, the winds should just come from north and south perpendicularly to the equator. Actually, that's not the case. Due to the rotation of the Earth, the winds are a little bit deviated. This effect is called the Coriolis effect. I made a small movie about it. At the equator, you see the spin of water at the equator, north and south of the equator.
we are doing some experiment. We are directly on the equator. So you see here 3 different bowls, one on the equator, one on the southern hemisphere and one on the northern hemisphere. And we'll pour water in it, and you will see on the northern hemisphere the water will turn clockwise. On the equator it goes down perpendicularly without any turning, and on the southern hemisphere it will turn counterclockwise. This is caused by the so-called Coriolis force. And you see the Coriolis force is turning in direction of the clock. Yes, it's clockwise.
So the farther you leave the equator, the more faster. The farther
Yeah.
the faster it becomes in speed.
You know this, if you empty the bathtub, you have this thinking in the north hemisphere, it goes in the direction of the clock. You see it turns. And we are here 5 meters away from the equator. So we go over here. So this is the equator here. People are taking photos. And here we are directly on the equator. First we go to the southern hemisphere. So now we are in the southern hemisphere. And we put some water here inside. Let us see. So now this should... So, okay. Starts turning. Put some flour in. So it should turn counterclockwise here.
So the farther you leave the equator, the faster, right?
Yes, but we are only 5 meters away from the equator here.
So let's go in the middle and see what happens.
So now we see the middle.
Yes.
So this is the equator here, 0 degrees latitude, and here is another getting filled up. We put in the separator. Okay, so the separator to have the same conditions as before. Okay. So let's see. The water goes out and no Coriolis force, and the flower stands still. Quite interesting. Thank you. Thank you. Thank you. Take a look here. This is our demonstrator. What's your name? Thank you very much. Thank you for joining. Thank you.
Wind speed distribution or wind frequency distribution, we can start same as for solar energy with an average irradiance or average wind speed here. So we have the relative occurrence h as a function of the wind speed v and multiplied by the actual wind speed added up, and then we have the medium wind speed or the average wind speed. The question is, why is that method not very helpful for wind speed? As we know, you can be applied for solar power, but for wind is less preferable. We will discuss this in the upcoming lecture. First, let's talk about the wind speed distribution or wind frequency distribution. If you take a look at the actual occurrences of wind speeds, you come to a so-called Weibull distribution, which is given in the formula here, K divided by C. Then you have wind speed V divided by C. C is a so-called scale parameter with the units meters per second, which is round about 10 to 15% above the average wind speed within a year. Then as the exponent you have K minus 1. K is the so-called shape or form factor, which is in the vicinity of 1 to 3 in Germany typically, and good conditions 2, and less good conditions 1. 3 never occurs in Germany, only in very wind-rich countries. There's no unit for the K. And that's multiplied by the exponential function with the exponent minus v divided by c and the exponent of k. You can also sum that up. So you have the sum of the wind occurrence, the integral of the frequency distribution. The formula is a bit changing. So you have then the integral from 0 wind speed to the actual wind speed in the Weibull function of that, and then you have as a function the 1 minus the exponential function v divided by c as exponent of k. Here you see some examples of wind power distributions or frequency distribution for the case of Germany. The wind speeds are measured in a height of 10 meters above ground level. So you see Berlin, it's not at the coast, so the conditions are less favorable. So the shape factor, a shape parameter, is even below 2, 1.85. We have the scale parameter, 4.4 meters per second, and the average wind speed of 3.9 meters per second. If you take very good conditions, the very last one, List Sylt, this is an island in the North Sea. So we have here as a shape parameter 2.15 and scale parameters of 8 meters per second and an average wind speed of 7.2. So we are still far away from the mentioned shape factor of 3 in Germany. If we know those Weibull parameters, there is a formula to translate it into the average wind speed developed by Molly. This is given here, c times brackets 0.568 plus 0.434 divided by k as exponent 1 divided by k. If we use k is equal to 2, which is very typical for Germany, then we have this formula. So this is 2 divided by the square root of p times the average wind speed. If we use c at 2 and k at 2, the Weibull transforms into the so-called Rayleigh distribution, which fits really well to the conditions in Germany and in many other countries. So this is our Rayleigh distribution, p half times wind speed divided by the average wind speed in square, the exponential function minus p quarter, v square divided by the average wind speed square. Here you see the effect of k. So as I mentioned, k is equal to 2 is very typical. So this is here in the rows. Here k is equal to 2, Rayleigh distribution. If you go to k is 1, then we have too much of low speed. If you go to k is 3, it's getting quite symmetric. These are the different Weibull distributions and the shape factor as a function here. Let's take a look at the Rayleigh distribution for different average wind speeds. So we have here the wind speeds of 3 meters per second, 4 meters per second, 6 meters per second, and 7 meters per second. You see how the form is changing. Let's calculate the actual power that is contained in the wind. So we have very basic formula of mechanics. First we come from energy is half the mass and velocity in square. And if we go to power, then we have the derivation of mass to time, m dot it's called, v square. If we substitute the mass stream m dot by the product of air density and the volume flow v dot, we have then p is half rho, well that's the air density, times v dot times v square. The air volume flow can be described by a flow through a cross-section area A, for example the swept area by the wind turbine with the velocity v. So we have then another v inside, and that's very important. So we have the wind particles sweeping to that cross-section area with a velocity of v, and we have the original v square we have from the upper formula. So at the end we end up with a cubic relation between the power and wind velocity. This is a reason why the average wind speed is not very helpful, because if you have a quantity of very large wind speeds, this power is weighted much heavier than if you have some wind speeds which have a very low wind velocity. So this formula is quite important. The power is half the wind density times the area where the wind is sweeping through times the velocity to a power of 3. Here again that formula, again also the air density. This is a function of temperature, of height and actual air pressure. Unit for it is kilogram per cubic meter. And as I already mentioned, A is the area swept by the turbine blades in square meters. One can derive the cubic relationship of wind speed V to P0 in the formula by the consideration that the wind flow is a series of air particles or air parcels which are hitting the turbine with their velocity v. Each of those parcels has the same energy, 0.5 mv square. Since the power is the energy received per time frame, we obtain a proportionality of the air parcel frequency to the wind speed. Together with the energy per parcel, we get P is proportional to v square times v, and therefore to the cubic velocity. The wind speed is changing due to the weather conditions, but also due to height. Here is a formula. If you measure at a certain height, for example, typically at 10 meters, but modern wind turbines are quite high, for example, 100 meters, so you can calculate that velocity in a certain height. This is a logarithmic function, so you have here, for example, v at h1 is the wind velocity at 10 meters, and then you have the boundary layer displacement, it's 0 to 0.7 meters. If you have heights of 100 meters, this doesn't play a role and can be neglected. Then you have another parameter which is called Z0. This is the roughness of the terrain. You get it via maps or tables. We will see a table later on. You put in the numbers and then you arrive, for example, if you have a Z0 of 0.1 meter and a D of 0 meters at this curve. For example, if you take a look, you measure, for example, at 10 meters, you measure a wind velocity of 6.5 meters per second. So you would have at 100 meter, you would have about 10 meters per second of wind velocity. So this is a table with the roughness values, Z0. So the C is very flat usually, and you have a very low C0 value. If you go to open terrain like pastures, you have a Z0 of 0.03 meters. If you have rough terrain, it's 0.25 meters. If you go to the city, it's even 2 meters. This is the air density as a function of height. So we have got the wind velocity as a function of height. Now we got the air density as a function of height. And also you see 3 curves at different temperature, because usually also with the height, the temperature is also changing. If you are at sea level, usually it's quite warm at sea level, you have here a density a bit above 1.15 kilogram per cubic meter. If the temperature is lower, for example in winter, then the air density goes up. If you go to a higher position, for example the mountains, the air density goes down. For example, if we take our 30 degrees value and we go up to 1,500 meters, then the density is below 1 kilogram per cubic meter only. That means also we have an accordingly reduced power output of our wind turbine. This is a formula for that here. It's a linear function, so you can use this function to get a good approximation for the actual air density at a certain height and a certain temperature. Also, air pressure is changing. So this is the air pressure at a certain height. This is an exponential function. As a parameter, you have the temperature gradient. If you go to the very last line here, you see that is a 0.0065 Kelvin per meter. Means the temperature is decreasing at height with about 7 degrees per 1000 meters, or 6.5 degrees per 1000 meters. And you have other parameters. You have R, the universal gas constant. You have the ground acceleration. You have the average molar mass. For example, for air, it's 0.02896 kilogram per mole. You have the air temperature at a certain height. You have the air temperature at sea level. You have the pressure both at sea level and at the certain height h. So some rules over the thumb for the power output of your wind turbine. So as I already mentioned, the wind energy or the wind power increases with the cube of the wind speed. 10% increase in wind speed translates into 30% more electricity or power output. 2 times the wind speed translates into 8 times the electricity. So therefore it's not very helpful to use these average data, because if you have a high value of the wind speed, they disproportionately produce more electricity. The height. Wind energy increases with the height to the 7th power. 2 times the height translates into 10.4% more electricity. As I mentioned already, this depends on this Z factor and so on. Air density, we saw the formula. The wind energy increases proportional to air density. That's not only a rule over the thumb, it's directly in the formula. Humid climates have greater air density than dry climates. Lower elevations have greater air density than higher elevations. We saw this also in the formula. The blade swept area. So wind energy increases proportional with the area. So it's directly proportional as we saw in the formula. 10% of increase in the swept diameter translate into 21% greater swept area and power output. Here we take a look at the possible extractable power from the wind. PN. So just take first a look at the picture here. So we have wind arriving with the velocity V1 and we want to extract power of it. So after the windmill, the velocity is reduced. While it's reduced, it also has to have a bigger area it has to cover. Otherwise, there wouldn't be any continuous flow of air there. The wind speed relevant for the extraction of power is the average between V1 and V2, here between those two, as a rule over the thumb. We have now the extractable power, which is half, then m dot, which is the mass flow, and then velocity 1 in square minus velocity 2 in square. So this is then the formula here, when they have here the air density and the swept area. Not A1 or A2, it's actually the area which is here in between. The only area we actually know, because it is our swept area by the turbine and the turbine blades. That's the formula. We want to find the optimum, which is the optimal, let's say, which is the optimal reduction of wind speed to extract the maximum power. For example, if we would reduce the wind speed V2 to 0, this wouldn't allow our continuous flow, because the wind parcels or wind particles have to get away from after the windmill. So this wouldn't be possible. If we have V1 is equal to V2, we wouldn't extract any power of it. So this investigation has been already carried out by Mr. Betz in 1926. So he thought about how we get the maximum power out of it. So he had the function called the power coefficient. It's the same as the conversion efficiency. So you have here the possible power of the wind, which you see in the lower part of the equation. So this is 1/2 times A times V1 to a power of 3. So this is the theoretical available power, and the actual used power is that one. Remember from the formula before, you can compensate lots of this stuff here, the air density, the area, the factor by a half. Then you end up at this formula, and we want to find the maximum of that efficiency function or power coefficient function as a function of not only one velocity, but the relation of V2 to V1. So how we do that, to get a maximum or minimum, we derive that function for V2 divided by V1, and we will find 2 0 points. So we use the product rule. So we derivate first part of the equation here multiplied by the original second part. Then we add, and then we take the original part of the first part of the function and multiply it by the derivation of the second part. This is done here. So you see here, first part derivated here is we derivate to V2 by V1. So derivation of that is 1. A 1 derivated to V2 divided by V1 is 0. So we have 0 plus 1. This second part stays original. This is G here. So this is the first part. And then we come to the second part. Then we have here this function stays the same. And the second part gets derivated. 1 is getting derivated to 0. And then we have a minus, because it's in square. So it gets minus 2 V2 divided by V1. And so we have this function then. This is a normal quadratic function here. 1/2 times 1 minus 3 V2 to V1 in square minus 2 V2 divided by V1. The 0 points, positive 0 points here at the relation if V2 is a third of V1 here. And if you put in that relation here, V2 to V1 is 1/3, then you come to a efficiency or maximum efficiency or power coefficient of 16/27. Here it's more in detail here. So you have here the quadratic function. This is a so-called midnight formula, we call it in Germany. So you have here the solution for that formula is that one. So you usually, as a student in Germany, you learn it by heart. And then you put in the components here. For A, you have here 3. For B, this is 2. And for C, it's -1. Let's put in the numbers. So you have here 2A is 6 here, and minus B is -2. Then you have in the square root, you have B square. So 2 in square is 4. Then you have here 4AC, so that is 4. A is 3. And then you have C, which is -1. Then you have here that formula, -1/3 plus minus, because there are two solutions for that equation of plus minus 1/3. While you don't have negative wind speed, the only solution is -1/3 plus 2/3 is 1/3 then. And as you already saw, this leads to 16/27 as a maximum for the maximum efficiency, which is close to 0.6. As it was discovered by Mr. Betz in 1926, it's called Betz power coefficient. The tip speed ratio lambda, this is a ratio of the linear speed on the tip of the blade to the actual wind speed. And the linear speed of a rotating object like the wind turbines is its angular speed times distance r, so the radius from the center of rotation. So we have here the tip speed ratio is omega, small omega, the angular speed, times the rotor radius divided by the wind speed or wind velocity. Let's do a short calculation for that. What is the tip speed ratio of a 20 meters diameter rotor rotating at 6 per second at 10 meters per second of wind speed? It's homework for you. Till the next lecture. So here we have the power coefficient or the efficiency as a function of lambda for various wind converter configurations. So here you have the Savonius rotor, which is very easy to do, but the efficiency is quite limited. This is the maximum is about 20%. Then you have the Darieux rotor, which is much better. And here a single blade rotor, the other configurations here. So as a general rule, you can say as higher as the lambda is, as higher is the conversion efficiency. Here, there's also a publication, German, so you see here the highest is single blade rotor with a tip speed ratio, but you don't see those wind generator very often, or let's say extremely seldom, because the mechanical stress for such rotors is very high, and so maintenance and costs are quite high. In the 80s, there have been very often two-blade rotors, but at the end, the Danish design with a three-blade rotor and an average tip speed ratio lambda is almost exclusively used now because the lifetime is very long and the maximum conversion coefficient is quite good. So you see here typical wind turbine curve. So you have here for the 8 megawatt power plant. So you see here the power coefficient here in red. So that's the conversion efficiency. Below 2 meters per second is 0 because the blade not have enough moment to bring the turbine to a turn. Then it goes up quickly. Then you have a maximum here at a wind speed of about 10 meters per second, and then the conversion efficiency is reduced. The gray curve is actually more important. That is actually the power output of the wind turbine. You see it starts also at 2 meters per second, then it goes up according to the wind energy contained in the wind, almost with a cubic form. Then you have some saturation after 15 meters per second, and then the power is limited. If you go beyond 25 meters per second, it even may be switched off. This is a E127 by the company Enercon. Here we have the occurrence in red. So you already know that's a Weibull distribution, while the higher wind speeds contain considerably more energy due to this cubic relation. The energy availability looks quite different from the frequency. So you see here even those wind speed above 10 meters per second occur quite seldomly according to this Weibull distribution. They are contribute most to the energy of that wind turbine. So you shouldn't neglect those parts because they contain a lot of energy. Also for the layout of your wind turbine, sometimes you have to limit the turbine configuration to a certain wind speed because otherwise the mechanical costs would be quite high, or the mechanical construction would be quite costly. But you have to keep in mind, if you have a wind speed available at high wind speed, they contain a lot of energy. You see here how the height as well as the average wind speed influence the actual generation costs. See, the most important factors is the average wind speed here. For example, here if we go to 8 meters per second, it goes down for a 75 meter tower. It goes down to in the vicinity of 2 cents per kilowatt hour. What we have nowadays is a variable speed configuration. So the wind turbine is constantly at different speeds to maximize its conversion efficiency and power output. And then the AC electricity from the generator, usually a synchronous generator, sometimes asynchronous generator. And this has a changing frequency, so you cannot directly inject it to the grid. First you rectify it, make DC power out of, and then you create AC, which is synchronized to the grid at a constant frequency. This is shown here at these units here. So this is an inverter here, as you saw from the photovoltaic, as you know from the photovoltaic section, and feed into the grid. This is simple for transformer. Usually the output voltage is in the vicinity of 700 volts. Usually you feed in a 20 kilovolt line, but this is country specific. And if you go to very large wind power plants, you can even go into the high voltage power grid. Here you see the planning of wind farms via a modern simulation tool. This already simulates the noise of the wind turbines as well as the power output. We see just a small movie about it. So here you see the cost development, unfortunately only until 2003. There was a kind of also saturation. They don't get much cheaper, not as the photovoltaics, which have a constant price reduction rate. You see here, for the example of Germany, that in 1990, a kilowatt of nominal power of wind power costed 1,600 euros, while it went down in 2003 to about 800 euro. And this is also, same as you remember from the examples of photovoltaics, is a function of the installed capacity. Quite interesting, for some locations you have a very good complementarity. We do an extra lecture of this, of the complementarity of wind and solar. And here, for the example of northeastern Brazil, so you have a very good complementarity, for example, to wind and solar, but also to other resources. For this example, northeastern Brazil, you see that there's most wind in September, but there's a very dry season, there is not much water, and so the wind power can help to avoid water scarcity and substitute the dry hydropower plants during that period. Some market data. So we see here the development of total amount of wind power capacity globally. You have also this compound annual growth rate here. So it started with 26%, then it decreased to 17%, and nowadays in the vicinity of 12% of growth per year. You also see here the share of offshore, which is almost neglectable before 2010, and now it's 2%, 3%, and now it's in the vicinity of 4%. The total power installed is in the vicinity of 650 gigawatt nominal power. Here you see the annual growth rates, Now we have a growth of about 9% of each year of installed capacity. We had last year, 2019, we have about 16.4 gigawatt with an offshore share of 6.1 gigawatt. I've got some new numbers on the installation of wind power systems up to the year 2021. Here we see the new installations. So we see here in the year 2020, we have got a total number of 95.3 gigawatts of wind power. And in the year 2021, there have been 93.6 gigawatt of installations, while 21.1 gigawatts of them have been offshore wind power plants. So you see the share of that increased very much. We will take a look in detail a little bit later. So let's see the total number of installation. So we have here the latest number for 2021. We had 833 gigawatts of total installations. Of them have been 57 gigawatts in offshore wind power. You see the growth rate. In the last decade, it stabilized at about 12% per year, the so-called compound annual growth rate. Let's take a look who installed most of the new installations. We saw by far leading is China with 42% of all onshore installation. We'll see later also the offshore installations, followed by the US. Even during the government of Trump, there have been tremendous installation in solar as well as in wind power. Brazil is on the third place with 5% of all new installations. Germany is nowadays only fifth. It has been once leading together with Sweden, which both have 3% of new installation share. Offshore, the lead by China is even more pronounced. 80% of all new offshore power plants are installed in China, followed by the United Kingdom with 11%, Vietnam 4%, Denmark 3%, Netherlands 2%. Germany isn't even on this ranking here, must be on the rest of the world. On the country share of total amount of installations, Germany installed a lot about 2 decades ago, so there is still on third place with 7%. Second place is the US with 17%, and China is by far leading with 40% of all wind power installation onshore. Of offshore, China is leading even more with 48% of all offshore installations are in China, followed by the UK with 22%, then Germany with 13%, followed by Netherlands and Denmark. We'll now see quite interesting graph on the energy transition. So there are a lot of jobs in the oil and gas offshore industry now, and this graph shows the transferability of those jobs into wind power jobs. So we see on the upper right side a good skills overlap, about 28%, which are categorized as business support, construction installation, marine and naval skills, facility management, electrical and cost engineering and estimating skills. Some skills overlap concern the maintenance, the mechanical skills, the business development, subsea and pipelines. Partial skills are hydraulic, process safety, planning, scheduling, commissioning, contracts, quality management, instrumentation. And little skills are sure directly related to oil and gas. That means a well intervention, well completions and well construction and so on. So what we see there is for some part a good overlap. So we have a lot of skilled people in that area. Also some things to consider if you want to carry out the energy transition. You have to combine several sources, and this gets rather difficult if you have fluctuating energy sources like wind and solar. You see here the impact on the energy system. So you have here the remaining power supply besides wind and solar and hydro isn't yet very flexible, and so you see here considerable overproduction. So the gray and end of the gray area shows the actual power production, and this red or rose line shows the actual need. So the production has been very much exceeded the actual consumption here. You can look it up for any date at, for example, www.agora-energiewende.de or at energy-charts.de, or from the government it's called smart.de, and smart written with a D, not with a T. The light blue is a contribution of wind power, and you see during these 3 days wind is by far the most dominating power source. You see also if there are surplus, is there some impact on the price, so there are even negative prices. Cannot change the wind, but we can change the existing power plants, and if they get more flexible, the negative prices can be avoided or almost avoided, so the additional costs for the use of wind power is then reduced. There's some literature to that. First is the one for Mr. Betz. The original book was from 1926, so it was a reprint in 1994. Then we have by Mr. Gasch and Mr. Zwele, it's in German here, about wind power. Then we have by Mr. Howe an English version here, Wind Turbines, Fundamentals, Technologies, Applications, Economics. Yes, these are other Germans here. And here you can find some data on the internet, the Global Wind Energy Council, www.gwec.net, or data from the World Wind Energy Association. We have two competing associations for the global wind power here. Compare this data, they don't differ too much from each other. That's it for today. If you liked it, give a thumbs up or take an abo. Thank you very much.